All right, so next up is binary ionic nomenclature. So here we're going to be looking at metal cations and non-metal anions. All right, so our ions are atoms or groups of atoms that have lost or gained electrons. So cations are positive. So cations have lost electrons. And anions are negative, so they have gained electrons. Okay, because electrons are negative, if I lose some, now I have more protons than electrons. If I gain some, now I have more electrons than protons. Okay? So our metals lose electrons. So metals are earlier on the periodic table. So metals are in group 1A, group 2A, group 3A. They have fewer valence electrons. When our atoms bond, they're trying to get to an octet, which is 8 electrons. And so for metals, what's easier is to lose a few electrons and have a full octet from the previous level than to try to fill up the one that they're on. And so our elements in group 1A, such as sodium, they have one valence electron because group 1A. And so they lose one electron and they become a +1. Because if you look here at sodium, okay, a neutral sodium has 11 protons and 11 electrons. Well, if I lose one electron, now I have 11 protons, but I have 10 electrons. And 11 is one more than 10, so I have a +1 charge. Magnesium is in group 2A. So our elements in group 2A, they have 2 valence electrons, and they're going to lose 2 valence electrons and make a +2 ion. So neutral magnesium, 12 protons, 12 electrons. I lose 2 electrons. Now I have 12 protons and only 10 electrons. So 12 minus 10 gives me that +2. Okay. My nonmetals, they're over further down on the periodic table. So for these guys, it's easier to gain a few electrons than to lose a whole bunch. So something like chlorine is in group 7A, where there are 7 valence electrons. Okay, if I need to get to 8, 7 plus 1 gives me 8. So chlorine is going to gain 1 electron. So neutral chlorine, 17 protons, 17 electrons. I gain 1 electron, now I'm 17 and 18 electrons. So now I have 1 extra negative charge. So my group 7A, they will gain 1 electron. My group 6A, they need 2 more electrons, so they're going to gain 2 electrons. My group 5A, they need 3 more electrons, so they'll make A -3. Okay, our ionic compounds are neutral, so we charge balance, okay, and they form these formula units. So if I look at our most simple example, sodium chloride. Sodium is a +1 and chloride's the -1. This one's easy. +1 and -1 already give me a zeroed out. +1 -1 equals 0. There we go, neutral. So my formula for sodium chloride is just NaCl. Makes it nice and easy. When I get to something like that magnesium, okay, with a chloride, well now I have something that's uneven, right? If I have a +2 on magnesium and a -1 on the chloride, those don't immediately cancel each other out. So let's do a charge balance. I have some number of magnesiums, each at a +2, plus some number of chlorides, each at a -1. Okay, so I have to pick a number that I can do a division with. This is easy because it's just 2 and 1, so my number is 2. 2 divided by 2 gives me 1. 2 divided by 1 gives me 2. So I need 1 magnesium and 2 chlorides. So my formula becomes MgCl2. Okay, so I get my neutral charge balance there. All right, now, when we start to think about just naming our ions, if I have a main group element in group 1A or 2A, or even group 3A, as long as I'm above the stair-step region, then my element becomes just whatever element ion. So sodium ion, calcium ion, aluminum group 3A, above the stair-step, +3, aluminum ion. Now, where things start to get interesting, though, is within our transition metals. So our transition metals in that middle of the periodic table, and then that stair-step region, some of the metals below the stair-step. These end up having variable charges. They don't have a fixed charge. And so something like cobalt. Cobalt sometimes likes to form a +2, sometimes likes to form a +3. So how do I tell those apart? If I just say cobalt ion, am I talking about a +2 or a +3? Well, I differentiate using Roman numerals, and the Roman numeral denotes the charge. So if I have a Roman numeral 3 for the cobalt 3 ion, I'm talking about the +3. If I have a Roman numeral 2 for the cobalt 2 ion, I'm talking about the +2. Okay. For my anions, they get the base name of the element plus IDE as an ending. So nitrogen, when it ionizes, becomes nitride. Oxygen, oxide. Sulfur, sulfide. Chlorine, chloride. So we still use that IDE ending. Okay, so here are some of the common monatomic ions you will encounter. Obviously, there's a lot more ions than this, but this is some of the common ones that you'll encounter. Okay, and so again, group 1A, one valence electron, they like to make that +1. Group 2A, they like to make the +2. Group 3A, they like to make the +3. Okay, and then when I get to my group 5A, so they like to make the -3. 6A, -2, and then I'll drag an arrow in here. Okay, my group 7A, 7 valence. They make that -1. Okay? All right, now, so under the stair step, we have a couple of species that do need the Roman numerals. That's tin and lead. Okay, and they like to do +2 or +4. Okay, chromium, even though I only have one ion shown there, it can do more than one, so we still use the Roman numeral. Manganese, still use the Roman numeral. Nickel, we still use the Roman numeral, okay? These are still transition metals. They still have a variable charge, even though they have one charge that we see more often than others. Now, there is an exception, though. Okay, our transition metal exception comes in with these three guys right here, okay? Silver, cadmium, and zinc. These are three transition metals that do have a fixed charge. Okay, so silver is always a +1. Cadmium is always a +2. And zinc is always a +2. So these are fixed charges. Okay, so these three do not need the Roman numeral, even though they're transition metals. So you just have to memorize these three and recognize that these three are an exception to the transition metal rule. They do not need a Roman numeral. The rest of the transition metals, we still need our Roman numerals. Okay. All right, again, when we form compounds, we're trying to be neutral. So this cadmium bromide, or not cadmium, I was just talking about cadmium, calcium bromide, it's a lot like the magnesium chloride in that I have some number of calcium at +2 plus some number of bromine at -1. I have to have that charge balance of 0. This became a 1, 2, which is why we get the CaBr2. Now, with aluminum and oxygen, when I make aluminum oxide, I have some number of aluminum at +3 plus some number of oxide at -2 has to equal 0. So what's my common number here? Well, it's 6. So 6 divided by 3 gives me 2. 6 divided by 2 gives me 3, which is why I get a formula that is the Al2O3. I need 2 aluminums, because that'll give me an overall +6. I need 3 oxides. That'll give me an overall -6, which gives me my charge balance of 0. Okay? When we talk about these guys, our ionic compounds, we say that they are in terms of formula units. So basically the formula unit is just the smallest ratio of the various different ions going together. Okay. So in actuality though, when I look at something like sodium chloride, I don't just have an isolated single sodium and single chloride ion. What I have is I have this whole lattice of sodium chloride, sodium chloride, sodium chloride that go out across it. So you can see we get a whole bunch of those all together. Okay, so when we name these, all right, we're going to have the name of the cation, which is our metal, and then that base name of the anion and that IDE ending. Or if it's a transition metal, we'll have the name of the cation, the Roman numeral denoting the charge, and then we'll have our anion with that IDE ending. Okay? So let's look at a few of these and start doing some examples. Okay, so calcium and bromine, we just looked at that. That was the +2 for calcium. So we got that. And this is calcium bromide. Okay, again, chemical names, not proper nouns, so we're not capitalizing them. Okay, silver and oxygen. So silver, again, Roman numeral not needed because it is a fixed charge. So silver is always a +1. Oxygen is in group 6A. We need 2 more electrons, so it becomes that -2. Okay, so I get some number of +1 plus some number of -2 to equal my 0. So it turns out I need 2 of the +1 and 1 of the -2 to give me Ag2O for silver oxide. Okay, potassium and chlorine. So potassium is group 1A. 1 valence electron makes a +1. Okay, chlorine, group 7A, needs 1 more, so it makes a -1. This one's easy. We don't need to write out our little equation because +1 and -1 already give us our charge balance of 0. So we're going to get KCl for potassium chloride. Okay. All right. Moving on. Aluminum, group 3A. So we're going to make a +3 ion. Sulfur is like oxygen. It's in group 6A, so we need 2 more electrons. We're going to get that -2. All right, so some number at +3 plus some number at -2 has to equal 0. So we'll get 2 of these and 3 of those. So we'll get Al2S3 for aluminum sulfide. Okay. All right, now we've got one with a Roman numeral. Okay, so lead, Roman numeral 4, which means it's a lead with a +4 charge. So we're going to get lead with a +4. Selenium, all right, is over there also in group 6A, like oxygen and sulfur. So it needs 2 more, so we're going to get an Se with a -2. So we're going to get some number at +4 plus some number at -2 gives us 0. Well, 4, can we divide 2 into 4? Yeah, we absolutely can. So we're going to get 1 of the lead 4s and 2 of our seleniums, because that's going to give me a +4 and a -4, which gives me my 0. Okay, so I'm going to get this PbSe2. Okay, and so my name is going to be lead 4 And when I write these out by hand, I put the bars over the top of them because that's the way I was taught. So lead 4, and then selenium becomes selenide. Okay, so lead 4 selenide. All right. Okay. So let's look at a few formulas and see if we can figure out the names. All right, so Na is sodium. Sodium's in group 1A, so we don't need a Roman numeral, so we can just name this one outright. So sodium and nitrogen gives me sodium nitride. Okay, now iron. Iron is in the transition metal area, so now I can't just name this iron chloride. I need to know which iron I'm talking about. So I'm going to have to check my charge balance. So I have 1 iron at some charge plus 3 chlorides, each at a -1 charge. Has to give me 0. So in order for this to equal 0, what charge does the iron need to have if I only have one of them? To get it to equal 0, this has to be a +3. So I can get a +3 and a -3 to give me my 0. So the name of this one is going to be iron 3 chloride. Okay. All right. Calcium, main group, don't need a Roman numeral. P is phosphorus, so this is just calcium. Phosphide. Okay. Pause the video for a moment. See if you can figure out the last two. All right, how'd you do? Should be cadmium oxide and lithium iodide. Okay. All right. Now, normally when we name these, we don't say, magnesium plus chlorine. We would just say magnesium chloride. So, given the names, let's figure out the formulas. Okay. So, magnesium is a +2, chloride's a -1. So to do our charge balance, we're going to get MgCl2. Okay, cadmium, fixed charge at +2, nitride, -3. To do our charge balance, we're going to need a +6 and a -6, so that's 3 cadmiums and 2 nitrides, so CD3N2. Okay, so same thing. Pause the video, take a moment, try these other 3, and then unpause. All right, so how'd you do? So potassium bromide, you should get KBr. Rubidium oxide, you should get RB2O. And for silver sulfide, you should get Ag2S. Okay, now we like the systematic names with the Roman numerals for the transition metals, but I would be remiss if I did not mention that common names are still sometimes in use. So I'm only going to test you on the Roman numeral versions. We're only going to use the systematic name. But the common names for the various different transition metals are still out. So I just want to show you. So what we used to do instead of using Roman numerals is we had to memorize all these different things. So if you had the lower charge state, it had this OUS ending. If you had the higher charge state, it had the IC ending. Now this was crazy because copper does a +1 and a +2. So +1 was cuprous, +2 was cupric. Iron does a +2 and a +3. So for iron, the +2 is ferrous and the +3 is ferric. Then you get to tin, does a +2 and a +4. So the +2 is stannous and the +4 is stannic. These just had to be memorized. When I was going through school, we had to know all of these Latin names, and for more than just these 3. I used to have these flashcards on a ring. We didn't have our, well, when I started college, I think I had a cell phone. Yeah, I think I had a cell phone that had 15 minutes a month of service. It was just for emergencies because it was the 90s. So we didn't have smartphones in our pockets. They didn't exist then. So I couldn't pull out my phone and do anything. So what I would do is I would make these flashcards and I would write all this stuff on these little flashcards that was on a ring, and I would keep that in my pocket. And when I would go out to dinner and we were waiting in the waiting room, I would have people quiz me. If I was standing in line at the grocery store, I would pull out my flashcards and I would quiz myself while I was standing in line on the grocery store. So we just had to memorize these. I'm not going to make you memorize them, but again, I'd be remiss if I didn't show you them. They do still exist. I've had students that have worked or interned in places where they've seen these. I have toured labs that have some really old bottles of reagents that still have the Latin names on them. So I want you to be aware of the fact that they exist. They are out there. They're just not used very often anymore. We've gotten really good at switching over to the systematic name and using the Roman numerals instead of having to memorize all of these. Just for information, here's a few more like chromis and chromic, mercurius, mercuric. So if you've ever heard those, that's where this comes from. It has to do with the Latin name, the original name for some of these elements, with a specific ending that has to do with, is it the lower charge state or is it the higher charge state? So that's what those are. Again, you need to know the Roman numeral method. You don't have to memorize all of these Latin names. I just want you to know that they exist in case you ever encounter them.